Lesson 82. We are talking more about limits, more about continuity, and differentiability. Okay, so the idea of, we talked a little bit about this, but what it means to be differentiable and when, most importantly, when it's differentiable. So, okay. Looking at part A here, I don't really have, I forget exactly how I have this lesson set up, but limits and continuity. Stating here, it is not obvious, but for a function to have a derivative at x equals c, then it is necessary that the function be continuous at x equals c. And we've talked about that a little bit, but just the idea here is that if it is, in order for there to be able to be a derivative, the function has to be continuous. Okay, has to be a smooth, continuous curve, and if that is the case, then it is what I would call differentiable, where you can take the derivative. So notice the slight comment here. It's saying if f prime of c exists, so if the derivative exists, then the limit of f of c as x approaches c is equal to f of c. So, and that whole idea that the limit equals the point is saying that it's continuous, right? Because remember, to be continuous, the limit from the left equals limit from the right equals the value at that point. And so this is saying the limit from the left and right equals that point. So if the derivative exists, this is saying that it is continuous. The existence of the derivative at c tells us that the function is, as I just wrote, continuous. Okay? Let's go down and talk here. B. Differentiability. A continuous function is not differentiable if the graph comes to a sharp point or has a vertical tangent line at value x equals c. We've talked about the sharp points before, I believe, okay, that if there's a sharp point, you can't take the derivative. So a sharp point, or you might hear the word cusp. Okay, we'll look at some pictures here in a moment. But sharp point or cusp, that means that your function is not differentiable at that point. You might be able to take the derivative everywhere else, but at that one point. Okay? Left-hand and right-hand derivatives must be equal in order for a function to be differentiable at a value x equals c. And that goes back to the whole continuous thing. Now, let's look at example 82.1. It says to use left-hand and right-hand derivatives to determine if this function is differentiable at x equals 2. So, left hand and right hand derivatives to determine if this function is differentiable at x equals 2. So this is kind of the proof behind it. Because what do you know about this graph?
It's a V that's right.
Okay, it's a V that's right too. Which the key is it's a V. So what's there going to be if it's a V? A sharp, hard point, whatever whatever vocabulary you want to use there. So if we look at this picture real quick, absolute value of y equals x says it's a V. The minus 2 in parentheses says it is a V that is moved 2 to the right. I think I made my V a little too vertical, but that's all right. Now, if we're talking about left-hand and right-hand derivatives, do you remember doing derivatives of something like this? We had to do them individually, right? So, what is this equation here of the right side of the V? We're just looking at the right side of the V. This is the equation of the line y equals x minus 2 is just the positive version of whatever's in the absolute value, correct? Now, what about the left version? Is this also y equals x minus 2? Right. If you recall, if you need help, I would write it as the negative of x minus 2, right? Like that's the idea behind it. It's the negative of x minus 2. But what you're probably more comfortable than is saying is negative x plus 2. So if we write this as I'm going to call it a piecewise function. F of x equals absolute value of x minus 2. Well, it's x minus 2 when the x values are what? Greater than 2. Could we also say equal to 2 there? Technically you can. Okay. And the other side of my line was negative x plus 2, and when is that? When x is less than 2. And officially we could say less than and equal to. Okay, so use left hand and right hand derivatives to determine if this is differentiable. So the equation on the left is y equals negative x plus 2, correct? What is the derivative of y equals negative x plus 2? Y prime is negative 1. What is that derivative evaluated at 2? It's still negative 1, isn't it? I mean, officially, I'm just doing what we have to do, which means y prime evaluated at 2 is still negative 1. Now, this is the left side, yes? So the left-hand derivative is negative 1. Okay, let's check the right-hand derivative. The right-hand equation is y equals x minus 2. What's the derivative of x minus 2? 1. What is the derivative evaluated at 2? Still 1. And this is your right-hand derivative. What did we just find about our left-hand and our right-hand derivative? They're not the same, are they? They are not equal. Because we just found that negative 1 on the left, 1 on the right, and I don't know about you guys, but any math I ever do, negative 1 and positive 1 are not the same thing. I would much rather have a positive dollar in my pocket than a negative dollar in my pocket. Meaning I'd much rather be up $1 than owe someone $1. Okay, so the question was, use left and right-hand derivatives to determine if this function is differentiable at 2. What do we know? We already knew it, but it's not, because the left-hand derivative and right-hand derivative are not the same. Then it's not differentiable. So I'm going to write it in words that this is not differentiable. Sorry, I have a problem spelling that word. You know, there's a lot of words you can just write. Are there some words that you have to like slowly kind of? Are you a Wednesday person?
Yes. I am too, even though it spells worse.
Okay, so I'm going to say not differentiable because the left and right hand derivatives are not equal at x equals 2. And this pen that I've been using forever is finally dying. Such a bummer. Okay, and I know, yes, you guys knew exactly what that graph looked like. There was no question really there because you knew that was a hard point, but there's kind of the work behind it. Okay, so those derivatives have to be equal for it to be differentiable. So, let's look at example 2. For what values of x is the piecewise function differentiable? Well, what do you know? Start plugging stuff in?
Yeah.
Cool.
Take the derivative of the two piecewise pieces.
Okay, the derivative of the two pieces. And as officially, we should check the whole thing, right? I mean, what do you know about x squared? It's a parabola. And a parabola, does that have any hard points or anything? No, so a whole parabola is differentiable, right? What do you know about the 2x minus 1? It's just a straight line, so that's differentiable. So what's the main question? Is it continuous? And? Yeah, we have to consider left and right, but it's not even so much about the limits as it is also about the derivatives. Okay, now we can, and I don't know that, I'm kind of getting the impression you guys don't want to, but I'm just going to have you think about the graph briefly, because here's the deal. Well, I guess we pretty much can figure out what this graph looks like. Because that helps you a little bit here. Okay, so if I pencil it in, what is y equals x squared? We said that's the parabola. It's going to go through what? 0, 0, and 1, 1, yes? That's just my penciled in parabola there. What is the line 2x minus 1? Okay, has an intercept of negative 1. Goes up 2 over 1, which means when it goes up 2 over 1, it's also going to go through the point 1, 1. Now, obviously, the entire parabola and the entire line does not exist, right? What was the key? The parabola is when x is greater than or equal to 1. So that is the right side of the parabola, yes? The line is when x is less than 1. So that is the line before. Now, that is me freehanding that, yes? That is not me trying to look on the graphing calculator and see, that's just me freehanding. Like the last graph, can you tell for sure what kind of point that is? It's hard to tell, right? And there could be some kind of curvy point there that could make it a hard point. There might not be. And so that's where we do need to look at our derivatives. So on the left, the equation on the left is y equals 2x minus 1. What's the derivative? 2. On the right, what's my equation? Y equals x squared. What's the derivative? 2x. Where are we concerned about this? At 1, right? At x equals 1. So, what is the derivative on the left at 1? Still 2, because the derivative is just 2. What about on the other side? Also 2, because 2 times 1 is 2. So we just found out derivative on the left is 2, derivative on the right is 2. And what do we know? 2 equals 2. So we just found the left derivative equals the right derivative. So for what values of x is this function differentiable? All real values of x, including x equals 1. So what that's saying is, however exactly this line and this parabola connect here, it's not going to end up being a hard point. Okay? So I'm going to say f is differentiable for all real values of x. And I'm going to say including x equals 1.
There's no supplementary homework.
There's one.
There's one. Not more, so
It's written here.
Gotta shut it for a second.
Huh?
I gotta shut it for a second. There, the 4 pages.
I have one written in there. I'll have to look at it to double check, but yeah, I have one written in there. Okay. Let f be defined as follows. F of x equals absolute value of x plus 3 when x is less than 1, and it's ax squared plus bx when x is greater than or equal to 1. Find the values of, guess what? A and b, such that f is continuous and differentiable at x equals 1. Okay.
I just got used to doing this, but with one value.
Can you visualize the graph here? Absolute value of x plus 3 is what? Say that again.
A v with an intercept of 0, 3.
Okay. A v with an intercept of 0, 3. So a v pushed up 3. Now, and when is that? That is when x is less than 1, correct? So this v that goes from the left, or goes from 3, oh, I meant to do that. Well, oh well. It goes left of the y-axis, and it does what? It goes over here to 1, and then notice it says x is less than 1. So at 1, we don't know, right? Now, and then what do you know about ax squared plus bx? It's a parabola. Since we don't know what a and b are, do we know what the parabola is doing? No. Maybe it's going up. Maybe it's going down. Maybe it's on the right side of the parabola. Maybe it's on the left side of the parabola and still going to go down and then up. Okay? In other words, there's a variety of, options. Is our parabola going to go up like that? Is it going to go down like that? We don't know until we know what A and B are, right? And that's our job, is to find values of A and B that can make this work. So, what are the pieces we know here? Or what are the things we need to consider and do? Okay, so you're just randomly saying come up with numbers that plug in to be the same thing, right? Now, here's the deal though. We can't just plug in any numbers because some numbers could possibly give us a sharp point. Okay? And they would appear to work, but they would give us a sharp point.
Use the limits to find what's continuous and then evaluate those if they're differentiable.
Okay, so think about, in order to be continuous, the limits have to be the same, yes? In order to be differentiable, what has to be true?
Derivatives have to be the same.
Derivatives have to be the same. Think we're going to gather some information by checking that out? Okay. Okay. So, you guys want to do continuous or differentiable first? Or does it matter? I don't know that it matters personally. So, differentiable is the one we've been doing, right? So, if we look at differentiable, our equation on the left is what? Absolute value of x plus 3. Wait a minute. Okay. I don't want... Well... Okay. Hold on. Here's where... Let me repause that. I forgot about a minor detail. We are looking specifically at where? At 1, yes? Over here doesn't really matter. Because we already know there's a sharp point right here, yes? We're trying to make this continuous and differentiable at 1. What is the equation on the left leading up to 1? Just x plus 3. Does that make sense? Because remember, when we do a derivative of absolute value, what do? We break it into a piecewise function. We're only worrying about at x equals 1. So we only need to talk about this right here. This line is a piece of x plus 3. Does that make sense? Sorry, I misguided us for a moment. So what is the derivative of x plus 3? 1. What is the derivative evaluated at 1? And it's still 1, right? And this is our left. Now, what is our equation on the right side of 1? Ax squared plus bx. What is the derivative of ax squared plus bx? Can you guys handle 2ax plus b? A and b are just constants, right? The x is the variable. So 2ax plus b. What is that derivative evaluated at 1? Put 1 in for x, and it's 2a plus b. And if this is differentiable, what do we know? Left has to equal right, and so 1 has to equal 2a plus b. So whatever we find about our a and b values, they have to satisfy the equation 2a plus b equals 1. Okay, that's differentiable. Continuous. So go back farther in your brains. I know Daryl mentioned it. If it's continuous, limit on the left equals the limit on the right, yes? So, we're doing the limit as x approaches 1 from the left of f of x. Well, again, what is that limit we're doing? Or what is f of x there? Limit as x approaches 1 from the left. The equation on the left is x plus 3. I have written down here absolute value of x plus 3, but it won't matter either way. And what is that limit? 4, right? You put in 1, and that's going to be 4. Now let's check the limit on the right. The limit as x approaches 1 from the right of f of x. Well, on the right, we're back to that ax squared plus bx. So the limit as x approaches 1 from the right of ax squared plus bx. Put 1 in place of x, right? That's a times 1 squared plus b times 1, which is a plus b. If it's continuous, the limit on the left equals the limit on the right. So if it's continuous, what is true? 4 equals a plus b. So I need values that satisfy 4 equals a plus b and 1 equals 2a plus b. You can eyeball it and try and figure something out. More officially, what works? Okay. You said plug it into the other equation? Yeah. Okay. So Nathan's on the substitution boat. Logan's on the elimination boat. Okay. Doesn't matter.
Elimination where you subtract the two equations?
Mm-hmm.
Okay.
I mean,
I got values.
no, you guys are good. The idea is we have two equations here. 2a plus b equals 1, a plus b equals 4. My brain sees elimination here. Nathan's brain saw substitution. Here's the deal. You're both going to get to the right answer. Okay, that's all that matters. So, Trevor, you're just asking, is this what I would see is, I would subtract these. 2a minus a is 1a. B minus b cancels. 1 minus 4 is negative 3. Okay? I'm not against substitution either, so. I think you're just against substitution because it's Nathan. So, if a plus b equals 4, negative 3, so that does make b 7.
I think it's something like self on the day of tests.
What'd you say?
I'm against the subs on testing. But then, like, the teacher asks a question,
Yeah.
they might have, like, on school, when you're not school kids, they hit scramble answers, and so now you have all the above as choice A.
I like it more than substitution.
But you know what that means.
But I don't like it when you have to get it into the That's what
Okay, I am checking one thing real quick. What are we in? 82.
And Spanish, like, it's not English, and so, like, answers will be wrong. I feel like sometimes, on a big test.
One of the AP class things, like those pretty simple things.
Okay. Number 5 is the one that's the question that number 5 is from 74. So that's what I'm trying to figure out what I'm doing with that one.
You can just skip it. Do like 24 problems is a nice. It's 24.
Well, if you
See, look at that.
It's better,
Probably some decimals in there. So,
probably, people.
Okay. Number 5 is the question that does not go. I have it written down as 18 from 74. I'll give you the option. If you want to look at 18 from 74, it's an integration problem. You can do that, or you can skip it.
I mean, I'll look at it. Whether or not I write something down is a different story.
It's definitely a good integration problem to be able to do. Okay. So it looked like, I think it looked like use substitution. Use substitution is necessary, though. You know,